Thanks, Tom, and thank you, everybody. It's really a pleasure to be visiting LASP to give this talk. I see a few people who know me, and they know I've been on perpetual travel with MAVEN, so that's not as far-fetched as it sounds. In fact, I look around and I see, surprisingly, several members of the MAVEN science team out in the audience. Bill Sonal, a couple others, Bill Postle. And to you guys, you're going to hear, Mike back there, you're going to hear some things that you know more about than I do. So if I say anything at all misleading or incorrect, please feel free to keep it to yourself. What I want to do is tell you about the MAVEN mission. We've been working on this since 2003. So that's 12 years. It was 10 years from what I consider to be day one till we got to the launch pad. And after a decade of giving talks on here's what we're going to do, it is incredibly exciting to be able to talk about here's what we're doing, here's the data we're getting back, and what it means. And I'm just beside myself standing up here able to talk about this. As an aside, this is the same talk I'm going to give tomorrow to LASP as a science talk, so you're seeing it before the rest of the lab is seeing it. I wanted to preview it to them first, but this talk came first on the calendar. What I'd like to do to begin, though, is to acknowledge somebody that has played a major role in the science that led up to MAVEN, but isn't here tonight, and that's Charlie Barth, who was the former director of LASP. He passed away last year, and he was the principal investigator and flew several ultraviolet experiments to Mars to study the upper atmosphere, starting with the Mariner 6 and 7 missions in the late 1960s. And it was that pioneering work, Mariner 6 and 7, Mariner 9, it was that pioneering work that really led to the ability to do a mission like MAVEN. The science has changed in terms of the goals, and I'll talk about that. But I owe a lot to Charlie, not just for setting up the science and getting it started, but he was the one who hired me over 30 years ago to come to LASP. So I have a great debt to him. I couldn't let tonight go by without mentioning that. But I want to start with what I think is a really exciting moment, and that's the launch of MAVEN about a year and a half ago now, November 18th, 2013. It seems like just yesterday. This moment really, a launch is a real milestone. We had 13,000 people come out to Cape Canaveral to watch that, and I see a lot of people in the audience who are out there. And it's a real milestone because it marks the last moment that you have a chance to do something to fix the hardware. After that, it's in space, and you have no opportunity except with software changes or course corrections. We've had our share of issues en route that cropped up, and we've addressed and resolved all of them so far, knock on wood. Launch is the single biggest opportunity to fail. Something like 1 in 20 or 1 in 30 launches doesn't go right. So that's a 3 or 5% chance of not getting to Mars after putting in a decade of work. I focused on the negative as we were leading up to this, and I remember, it's hard not to. You do so much of what NASA calls risk mitigation, where you try to think of the worst things that can happen, and then you fix them ahead of time. So I spent a lot of time dwelling on what could go wrong. And I think this rubbed off on my wife, because she told me that she was out on the causeway watching the launch thinking, my God, how are we going to console him tonight at a party we're hosting for 200 of our friends and family when the thing blows up on the launch pad? Fortunately, it was a picture-perfect launch. It went off. We had a 3-week period in which we could launch, and every day there was a 2-hour window. And it went off at the first moment on the first day of that 2-hour window that it could. So the weather cooperated, the technical side cooperated, and it was on its way. The launch of MAVEN also marked a real shift in how the mission team operated. Up until then, I'm the principal investigator of MAVEN, so nominally I'm in charge. I worked very closely with our project manager, David Mitchell from NASA's Goddard Space Flight Center. He was really in charge of the day-to-day operations. He'd been through this. He knew how to develop a spacecraft mission, how to work all the issues and make sure it launched on time. He was the one who got called up in the middle of the night first and would decide whether I needed to get called up and awakened. And that did happen, both of those. And once it launched, and once we got to Mars, it shifted. All of a sudden, it stopped being a development project where we're trying to get there. All of a sudden, we're there, and we're doing science. And it's my responsibility to herd a 100-member science team, people who come from academics and are not used to being directed. People use the... That's Bill, who's one of the members of the science team. People have used the phrase herding cats.
That's right.
What I want to do is talk a little bit about why Mars, about the development of MAVEN, and then about the operations and the science coming out of it. MAVEN is the Mars Atmosphere and Volatile Evolution Mission. And I've taken a lot of grief over the acronym because it's not a perfect acronym. The N at the end of MAVEN is the N at the end of evolution. So it's not quite perfect. People that care about these things have given me grief. And there's some reality, because the key to success in a spacecraft mission is picking a cool name. And all I can say about MAVEN is you should have seen the ones we didn't pick. So Mars is a place that has fascinated people, and I just picked up a random assortment of things out in the public eye about Mars. There's a music group called 30 Seconds to Mars. This was a photo taken by my wife in Estonia when she was visiting there, and they were performing. It's like, my God, I can't get away from this anywhere. You go to Eastern Europe and you can't get away. The Face on Mars, Life on Mars, which I've forgotten now if it's a British TV show or a British music group, but one or the other. Some of you will recognize this picture in the bottom middle. Any of you know what that is? Yeah. If you know what it is, I don't have to tell you. If you don't know, I'm not even going to try. Why Mars? Why is Mars such an interesting place? Let me start with where Mars is. Mars is the next planet out in the solar system from the sun. It's about 1.5 times as far away from the sun as the Earth is. It's about half the diameter, 1/10 of the mass, give or take. Its atmosphere is about 1% as thick as the Earth's atmosphere. Because it has such a thin atmosphere, because it's so far away from the sun, it's cold, it's dry. There's no chance of getting liquid water flowing at the surface. And despite that, we think that there's been liquid water flowing at the surface. And I'll talk about that in a minute. I had to put the labels on here because too many of the CU undergraduates would look at this and they couldn't tell which one was Mars and which one was the Earth. I'm sorry, I thought there were no CU undergrads in the group here. To my mind, the overarching question about Mars is whether there was ever life there. And the reason we think it's not a stupid idea is that Mars has all of the ingredients that would be necessary to support life, or even to support an origin of life. Liquid water, access to all of the elements out of which you would build life, things like carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus. I'm trying to run through the acronym in my head. Calcium, iron, and about 20 other elements. All of these are present in a geological environment on a planet that has an atmosphere. And then there's a source of energy that can break these things apart from the molecules that they're in and recombine them. That is, there's a source of energy to drive chemical reactions that would support metabolism. On Mars, a lot of that energy is interactions between water and rock. If you have water, you have rock, they're going to chemically react. This is a picture of one of the meteorites from Mars. This one is called Allen Hills 84001, ALH 84001. It was picked up off of the Antarctic ice in 1984. It happened to be the first meteorite collected that year. And the picture on the right shows why this one is of interest relative to life. And that is, they saw things in it that they thought were very reminiscent of fossilized microbes. Most scientists now think these were contamination, but the evidence says that water flowed through this rock, and that therefore, within that rock, you've met all of the ingredients necessary to support life. So it's not a stupid idea that there could be life. So the overarching question in my mind is, did Mars ever have life? If it did, how did it interact with its planetary environment? And how is the habitability? How has that environment changed over time? Those last questions about the change over time are what lead me to the MAVEN mission. And we're going to talk about that. We see evidence in the picture on the left here that liquid water has flowed over the Martian surface. This is what looks like a river system, a system of channels, of valleys that look like they were carved by water flowing over the surface. The water carves a channel, small channels coalesce into bigger channels as you go downstream from upper left to lower right. If there was water on the surface today can't hold water. The atmosphere can't hold water. It's too cold, too dry. So where did the water go? Where did the carbon dioxide that must have formed a thick atmosphere that would have warmed temperatures, a greenhouse atmosphere, where did the CO2 go? And there are two possibilities, and I've illustrated them both here. One is the volatiles can go down into the crust. They can go down out of the atmosphere into the subsurface and be locked up. And that's represented by this photomicrograph from that same Martian meteorite, the Allen Hills meteorite, showing these deposits in the middle that are carbon-bearing minerals and suggests that the carbon came from the atmosphere. We don't think that there was enough CO2 locked up in deposits like this to account for an early atmosphere. By the way, I've mentioned this idea of Martian meteorites. It's surprising to some people. We have meteorites in our collection here on Earth that have come from Mars. And the geochemical evidence is absolutely compelling. They must have been rocks on the surface that were knocked into space when an asteroid came in, hit it, and knocked it off. And they found their way to the Earth, where we've collected them and found the geochemical evidence that says they're from Mars. If anybody's interested, I can go into the reasons why we think they're from Mars, but I find it absolutely compelling. There are close to 100 of these Martian meteorites now. One of the interesting things, as an aside, is you can buy pieces of these from meteorite dealers. And when I became convinced that these meteorites were from Mars, I decided I had to have a piece. So I went out and bought one. The going rate, I have a piece about this big. The going rate at the time, maybe 15, 20 years ago when I bought it, was $100 a gram. And I figured that this was much more cool than what some of the CU students would spend $100 a gram for. I'm sorry, was that out loud? Anyways, the long digression for a lousy joke. Tom is sitting in the back, who introduced me, going, I've heard this joke before. The CO2, the water, can go down into the crust. It can also go up to the top of the atmosphere and be lost to space. The solar wind can strip it off. This is an image, a false color image of data from the European Mars Express spacecraft showing ions that have been stripped away from the atmosphere and are being carried away by the solar wind. In essence, that's what MAVEN is designed to measure. How effective the solar wind is at stripping gas away. We know it happens, but we don't know enough about the rate at which it happens, or what drives it, the processes responsible for it, or how much gas has been removed over time. And that's where MAVEN comes in. We're trying to understand those processes that drive escape. Now I'm going to go through this chart in incredible detail. We're going to spend the next 2 hours on this. Not really. I'm not going to go into it, but I wanted to make a point that what we're looking at with MAVEN is energy coming in from the sun. It can be in the form of the solar wind, or of solar storm events, or solar extreme ultraviolet photons, light, that comes in here from the upper left. And then what does it do when it hits the upper atmosphere? This is a cartoon showing all the different processes that we think can go on to strip gas from the atmosphere, and we're going to make measurements that tell us how these work and how they might have operated through time. And I want to go through one as an example, and that's the ability of the solar wind to strip away gas. And I picked this one because I've got a cool video that shows how it works. That's the important thing here. This is a computer simulation showing what happens when the solar wind hits Mars. The white arrows represent the solar wind streaming by from right to left. The colors represent the extremely tenuous gas in the upper atmosphere that's being stripped away by the solar wind as it goes by. It's an incredibly complex process, and we want to make measurements that tell us how that works. The solar wind stripping away gas, I tried to think of a good analogy of what that is, and it's like when you step out of the shower and you have wet hair and you go outside and the wind is blowing and the wind just strips the water right out of your hair. It's very similar to that. Mind you, for me, this is becoming a bit more of a theoretical exercise. Thanks for that pity laugh. So I've told you about the science and what we're trying to accomplish. I want to now talk about the spacecraft and the instruments. We designed a spacecraft specifically to do this mission. We didn't find one off the shelf. And this is the MAVEN spacecraft. It's an artist's drawing of it, so it's not a photograph. To give you a sense of scale, from left to right, one end to the other is about 37 feet. The high gain antenna, which is the round thing in the middle, is 2 meters across. So that's about this high, from floor to this height. The instruments are mounted either around the antenna, on the body of the spacecraft, or on booms. There are 1, 2, 3 booms that stick out. And then there's what we call an articulated payload platform, APP, that sticks down on the bottom. And there are 3 instruments on a platform that can rotate this way and this way. So while this points at the sun, the instruments on the platform can point at the planet, or point in the RAM direction, the direction the spacecraft is traveling. So we're able to make all the measurements we need. It's solar powered. You can tell that from the solar panels. We also have magnetometers way out at the far end, trying to get as far away from the spacecraft as possible, because they don't want to be measuring the magnetic field of the spacecraft. A better idea of the scale, tip to tip, it's about the length of a school bus. Now, mind you, it's not you wouldn't say the spacecraft is the size of a school bus. The bus itself, the bus of the spacecraft, not the bus of the school bus, but the cubical thing in the middle is called bus, and that's about 7 feet on a side. So here to here, square, and about this tall. Fully loaded with fuel. I passed by it, but the whole thing weighs about 2,500 kilograms. 1,600 kilograms of that is fuel, most of that to get into orbit. It's the same weight as a fully loaded GMC Yukon, which is the heaviest SUV on the roads. I had to look that up on the web. You can find anything. And the comparison is with MAVEN fully gassed up, with the Yukon fully gassed up, but also with 4 adults in the front and a couple hundred pounds of camping gear. So not quite as heavy as you can get it, but close to it. We have 9 instruments on the spacecraft, and I show pictures of them here. I've grouped them together. The ones in yellow are designed to measure the properties of the sun and the solar wind as it comes up and hits the planet. And because we're trying to look at the role that the sun plays on escape, we're especially interested in what that energy input is. The ones at the bottom in red measure ion-related properties, the composition, the speed, the direction in which ions are moving, because we think that ion loss is most important. Then we also have a magnetometer to study the interactions between the solar wind and the upper atmosphere. And then we have 2 instruments that tell us about the basic composition and structure of the upper atmosphere, and also measure, for those of you who understand it, isotope ratios that tell us about the evolution. One is a mass spectrometer. That measures the composition of gas at the location of the spacecraft constantly, and then an imaging ultraviolet spectrograph that measures the composition of the gas by looking at light emitted by the gas, and it lets us do it by remote sensing. So we get detailed point measurements from one instrument and global remote sensing measurements that are very complementary to it. As an aside, the imaging ultraviolet spectrograph, half of the Langmuir probe, and the EUV instrument were built here at LASP. 4 of the instruments were built at University of California, Berkeley, and the remaining 2 at NASA's Goddard Space Flight Center. And I may have forgotten to say this, the spacecraft itself was built at Lockheed Martin, about an hour south of here, the other side of Denver. Let me talk about the development of the spacecraft. We're seeing a couple of pictures, one early in assembly and one later in assembly. Early you can see the basic structure of the spacecraft and that cylinder in the middle that provides the real structural support when it gets launched houses the fuel tank. You can see the spacecraft being lowered down over the fuel tank. This was the last day anybody's ever seen the fuel tank. It was inside and invisible. Then in the lower picture on the lower right, that's with all the electronic components installed, essentially fully assembled. You can see the high gain antenna. If you're up close, you can see the reaction wheels that will spin in order to rotate the spacecraft. They're in this bay. In some of the other bays, they have the plumbing and the electronics, the computer that controls it, the plumbing for the propulsion system, and so on. The high gain antenna is on here. The high gain antenna came on and off during the whole assembly. Here the solar panels are not on, but they were put on for testing. And in fact, once it's assembled, testing is incredibly important because you want to make sure everything works right. Once you launch it, you don't have a chance to go back and fix a problem, so you try it out on Earth. You don't want it to do anything in space that it hasn't already done on Earth, because on Earth you've been able to test it and watch it and fix the problems. Here, for example, is a test of the deployment of the solar arrays. We probably did 4 or 5 or 6 tests of this, because if they don't deploy, we're dead. When we launch, they're folded up against the spacecraft in order to fit inside the fairing, and the active surface is on the inside. And the first thing that happens once it launches is you have to open the solar arrays and find the sun and orient toward it. And then once you are power positive, you can do things. As an aside, we launched it, and it took an extra half hour or so to ensure that we were power positive. And until that happens, we aren't sure the solar panels are open. When it comes off the launch vehicle, the spacecraft is tumbling. You know, it's just ejected. And it opens the first thing it does is it damps rates, then it opens the solar panels. Then it starts looking for the sun. And it has an algorithm it uses where it starts searching. And it turns out it started searching in this direction, gave up, started going back. And to do that, to go 180 degrees, takes about 20 minutes. So it was half an hour before it found the sun. We were sitting there sweating bullets till it did. Because if it doesn't, it has about 4 hours or 5 hours before it runs out of battery power, and then that's it. The other test that you saw, you can just see the tail end of it, is the spin balance test. For that one, you spin it in order to see where the center of mass is. Because when you put it on top of the rocket, you don't want it to be skewed one way or another. When you're controlling it, you need to know where that center of mass is. If it was off center, they were going to put weights on it to balance it. So it would be centered right on the top of the rocket. With all the testing, give you an example of why you need to do the testing. We spent 2 or 3 months doing testing, and I would say we found something like 1,100 problems, and every one of them had to be fixed. That sounds like a lot, but that's really typical of any spacecraft. The other interesting number I'm going to throw out at you, something like MAVEN is too complicated for anybody, any one person to understand the whole thing end to end, all the subsystems. So nobody can say, well, clearly that's going to work and that's going to work, so they're going to work together. The way you do it is you write down requirements. What does the spacecraft need to do in order to succeed? To do that, what does the computer need to be able to do? What does the fuel system need to be able to do? And if you make a system, build a spacecraft that meets all the requirements, more or less it'll work right. We had over 10,000 requirements, and each one had to be verified before launch. That is, somebody had to go back to the test data and look, redo the analysis, re-examine the data to make sure that it would work before they could verify. Somebody had to look at each of those 10,000 requirements. This can sink a spacecraft. You all know the Curiosity rover that's roving around on Mars. They were lagging behind in getting their requirements verified. They were building up what people call a bow wave of paperwork. And you can't launch till the paperwork is closed out. And they were frantic at the end. They were adding staff right and left, and they barely got the requirements verified before launch. They would not have launched if they hadn't verified it, because if you haven't, you might have missed something, and you don't know if it's going to fail or not. Our project manager was way on top of this, so it worked out really well. Once we did all the testing, we shipped it down to the Cape. It launched from Cape Canaveral Air Force Station down in Florida, adjacent to Kennedy Space Center. This is in its shipping box on the back of a truck. First thing we did, we took it out to Buckley Air Force Base, put it in the back of a C-17, flew it down to Kennedy Space Center. The way I think of it, when I was standing there watching it back out of the, well, pull out of the garage forward, I realized that it's like when you go on vacation. The vacation doesn't start when you get to the beach in Cabo. The vacation starts when you get in your car and back out of the driveway to go to the airport. And seeing the spacecraft on the back of the truck pulling out of the garage at Lockheed en route to the airport, I realized this is the first moment of its trip to Mars. It just took 3 months from then until launch, because once it gets down to Florida, first you have to make sure everything still works. So we did a solar array deployment test. We ran through all the science sequences. The spacecraft thought it was in orbit around Mars doing science. It went through everything. Once we confirmed everything, and by the way, once we survived a government shutdown, I don't know if you guys remember that. That was the year the government shut down for 17 days. And MAVEN is funded by NASA, Kennedy Space Center, government contract. We were shut down too. Fortunately, after 2.5 days, they started us back up. Somebody came up with the idea, well, the only way you can continue working if you're government during a shutdown is if you're saving lives or property. And someone came up with the idea that by sending us to Mars, we were saving property, the Curiosity rover, because we were acting as a relay for it. And we could make sure that it survived. I was worried that that was the goofiest idea I had ever heard. And I was afraid that somebody would realize how silly that was and shut us down again. And I really worried when I started hearing that congressional staffers were asking questions about this. But after another day, I think we were the first government program started back up. And after another day, Chuck Hagel called back 300,000 Defense Department employees using the exact same rationale. So I figured, okay, we're off anybody's radar screen. If we had shut down for 17 days, we would have had a very good chance of missing our launch window, sitting on the ground for 26 months before we have another chance to launch to Mars. In fact, it's worse than that, because we would have had to wait 26 months. But a launch 2 years later would have gotten us to Mars in a poorer opportunity, and we wouldn't have had enough fuel to get into orbit and even get down to our mapping orbit, let alone to carry out our science mission. So I'm sort of glad it worked out the way it did. Once it was all tested, the spacecraft was put inside the fairing that would protect it while it traveled through the atmosphere. The fairing was carted out, not that fast. This is speeded up. Really slowly, in fact. It was taken out at night because as soon as the sun came up, the winds picked up. You can see the shirts, the flags blowing in the breeze, and seeing this thing swaying back and forth as they're hoisting it up is not something I would recommend. It was put up onto the top. Everything was connected. 2 days before launch, the rocket and spacecraft were taken out to the launch pad and ready to go. The day before launch, we were able to get the whole team out there for a team photo in front of the rocket in the upper left here. And you can see the rocket in the back. You know, everybody wants to go to the launch. It's a really cool thing. It's an exciting thing to see. We had this is mostly science team because the ops team were working. And there's also an ops team at JPL. There was the navigation group at JPL and the ops team in Denver. The spacecraft was controlled while it was on the ground by a team at Kennedy Space Center because everything was hooked up. The moment it lifts off, control reverts back to these guys at the facility down at Lockheed to control it. There's an interesting story there. Once the clock gets to T-minus 10 seconds, in practice T-minus 15 seconds, the ops team is done. Nobody can call a hold. Even if somebody sees something fall apart, only the computer can call a hold at that point. So the team is done, and they had planned, the ops team at Kennedy had planned to all get up at that point from their consoles and run outside so they could watch the launch. And that's a perfectly reasonable thing to do. You want to see it with your own eyeballs. We had a number of rehearsals of the countdown, all the way that included fueling the rocket to make sure everything is going to work right. And one of the engineers said, you know, shouldn't we practice running outside? It seems silly, and they didn't. But then when it came time to run outside, he said it was exactly like a Three Stooges movie. They all bunched up in the door and couldn't get through it. They did manage to get outside. They did see it. It was a picture-perfect launch. We were right down the middle of the pipe in terms of where we needed to be. And we are at Mars. Here's a picture of the launch, November 18th, 2013. When we launch, we actually go into an orbit around the sun. And it's a ballistic cruise. We just get into an orbit and we cruise out there. When we arrive out at the distance Mars is from the sun, we've timed it so Mars is there. And we have 3 weeks during which we can launch and still get there. We go into orbit with we went into orbit September 21 with a 33-minute rocket motor burn. And that used something like 90% of the fuel we had taken with us just to get into orbit. By the way, this picture is not to scale. That is not the size of Mars relative to the spacecraft. However, this one is to scale. It's the final mapping orbit we're in relative to Mars. At the lowest altitudes, we're 150 kilometers above the planet. At the highest altitudes, we're a little over 6,000 kilometers above the planet. And that means that every orbit, we pass through the entire upper atmosphere and can make measurements. And then at the top of the orbit, bottom of the slide, but top of the orbit, we can image the whole planet with the ultraviolet remote sensing instrument to get a global perspective. So it's, I think, a very powerful combination. So I've told you about the science. I've told you about development, about how the mission works in terms of its architecture. And I want to tell you a little bit about the science, because that's really the fun part. And I've taken way too much time telling stories that aren't science. So let me talk about the science return. We're 5 months into the primary mission, the science mission. The first thing that happened after we got into orbit was we had an encounter with a comet. Not what we expected. Comet sighting spring was discovered in early 2013. And when they discovered it, Earth-based telescopic astronomers, they discovered that it was going to pass very close to Mars. On this picture, it looks like it hits it. And for a while, they were worried it would. It passed 140,000 kilometers away from Mars. That is nothing on the scale of the solar system. And we were worried we would get hit by it or get hit by dust from it. And the comet orbit was inclined and backwards relative to Mars orbit, so they're coming almost not quite head on. So any dust from the comet that might have hit our spacecraft would hit it at 56 kilometers per second. You can imagine we were worried. We had some early discussions about should we put extra blanketing to protect the spacecraft? Should we not launch? Is the risk too great? We did launch, however, we took precautions. We phased where we were in the orbit. We could adjust that easily so that during the peak dust risk, we were shielded from the dust by the planet. And we turned the solar arrays sideways to the flow to minimize our cross-section. We turned the instruments off so that we would minimize any damage. Once we survived, we turned the spacecraft back to Earth to communicate, confirm that it was okay, confirmed that the instruments were okay, and we wanted to look at what the comet had done to Mars. First, here's a picture of the comet taken from an Earth-based observatory. It looks like a comet. This is a picture taken by MAVEN 2 days before the encounter at a wavelength where we're looking at hydrogen. So we're seeing the hydrogen cloud surrounding it. The mist distance from Mars was about from here to here. So well within that cloud. So we could see right away that there was stuff that would hit Mars and hit the spacecraft. We wanted to see what the effect on Mars was. And as soon as we could look, we did that. And we looked and saw an effect with two of our instruments, the ultraviolet instrument. If you can see this blue line, it's the ultraviolet spectrum before the comet encounter, and this red line is afterwards. And even I can see these bumps that weren't there before that appeared there. They are due to metal ions in the upper atmosphere, magnesium and iron ions. The dust coming in at 56 kilometers per second hits the atmosphere, and that's fast enough, it vaporizes just from the friction passing through it and ionizes. Magnesium and iron aren't anything special. You know, they're parts of dust. They're geologic materials. Magnesium oxides, iron oxides. But they're easy to see on the ultraviolet, so they're what was detected. From looking at the emission and mapping it over the globe, you could determine how much dust must have hit the atmosphere, and it was roughly 5,000 kilograms. And I can't do that in my head, but that would be the equivalent of taking a boulder about half the size of this room, breaking it up into fine dust, and spreading it over the planet. Not a lot, but enough to create a new layer in the atmosphere. This was also detected by the mass spectrometer, which detected not only magnesium and iron, but titanium, aluminum, chromium, a total of 11 different ions. So we discovered a new layer in the upper atmosphere. This layer disappeared, this layer in the ionosphere disappeared after about 2-3 days. However, when we went lower into the atmosphere, we discovered a long-lived layer of dust from the same source, but not just from this comet. This was 4 months afterwards, from all sorts of debris coming in. We have measurements in that circle up there that are telling us about iron ions, and the mass spectrometer measured here shows 2 different isotopes of iron ions. So we're seeing the same sorts of dust, but at lower altitudes where it creates what we think is a permanent layer in the upper atmosphere. So we discovered a temporary layer, we discovered a permanent layer, and there's one more aspect of dust that I want to talk about. One of our instruments is able to detect dust if it hits the spacecraft. There's always dust in space. It's not a clean place. And if it hits the spacecraft at high velocities, it will ionize and change the electrical potential around the spacecraft. This is dust that is not big enough to cause any damage, but it's big enough to be detectable. And it doesn't create a pretty image, but here's an example of measurements of the dust. This is a graph from 100 up to 6,000 or 8,000 kilometers, and at different angles around Mars relative to the sun. And all of these colored dots represent dust hits. The gray represents places where we didn't detect dust. So we've discovered a layer of dust, or a cloud of dust, in orbit around Mars. This was unexpected, and we still don't understand it. We don't have a complete picture of it yet. All that white space is where we don't have measurements. We can't tell if the dust is dust from the atmosphere that is somehow being lofted up to altitudes where it doesn't belong, or if it's dust knocked off of Phobos and Deimos, the moons of Mars, that is coming down to altitudes where it doesn't belong, or if it's coming from outside of the Mars system entirely. This is one of the real puzzles. So I'm going through discoveries, and what has gotten the most attention is the discovery of a diffuse aurora around Mars, and we have a couple of the people who've done all the work in the back. And I think you guys wanted to applaud when I showed this image. We want to applaud you for the work to see this. Aurora on Earth come from electrons that are trapped in the Earth's magnetosphere and whip around from pole to pole. And if they have enough energy, they come deep enough, they can hit the upper atmosphere and cause it to emit light. What we're seeing here in the bottom, I'm not going to work through this spectrum, but the middle one shows the spectrum of the aurora. We're seeing it from the same cause, electrons, except except Mars doesn't have a magnetic field, so the electrons don't go from pole to pole at high speeds. Instead, they come straight in from the sun. The picture in the top shows how the image was, how the measurements were made, looking at the limb, looking at light from it. And the bottom map shows where the aurora was observed. It's diffuse, spread out over the entire northern hemisphere. This was an aurora observed during 5 days in December, just before Christmas. So the IUVS lead has dubbed it the Christmas Lights Aurora, because that's when you turn your Christmas lights on. He isn't like me. I keep mine on pretty much all year round. The aurora is shown in the top here, 5 days where you see that bump. And it corresponds exactly with the biggest storm of solar electrons that we saw coming in. So we have the smoking gun. We have the driver of the aurora, the electrons, and we have the aurora. So it's a complete picture of how this works. This is something that seems to catch everybody's interest. Personally, sorry guys, personally I think the dust is more exciting, but this is what really gets people's attention. You didn't see it. He stood back there and So let me talk about escape, because what we're trying to do is look at escape of gas from the Mars atmosphere. On orbit 1, we wanted to get the instruments on as quickly as possible because we were in the highest altitude orbit we were ever going to be. On orbit 2, we did a rocket motor burn to lower the orbit, to start getting into our mapping orbit, and we're never going to be that high again. And we got images of the hydrogen, oxygen, and carbon clouds surrounding the planet. These are important because these are the atoms that come from water and carbon dioxide, which are the two most important climate-related gases. They get broken up by sunlight, they move up to the top of the atmosphere, and from there they can escape to space. So we're seeing the atoms as they're in the process of escaping. This is what we set out to measure, and it was really heartening to see this and understand that we would be able to understand, we understood that we could understand how the gases escape. Understand? Bill does. So we want to understand, we want to learn how the solar wind drives this escape, and we're measuring the incoming solar wind. This is a representation of that. The sun is way off on the right somewhere. The solar wind streaming from your right to left. When it gets to Mars, it sees that obstacle, and it creates what's called a bow shock. Think of it like the bow wave in front of a boat. That's the first, when the solar wind hits that bow shock, it's the first indication it has that there's a planet there. And we're seeing here that the density of the solar wind increases. You can see the blue go to green as it passes through that bow shock. And the temperature increases. We want to understand what happens when the solar wind hits the planet. There are a couple of different ways in which gas can escape. If you look at this top panel, you see arrows that look like hair coming down off the bottom and arrows going straight back. The solar wind again is coming right to left, and by different processes it drives some gas downward and out, and other gas straight backward. We wanted to look for this polar plume, the gas going downward, and our orbit was such that we could look. It could either go downward or upward, depending on the solar wind conditions. Our orbit was such early in the mission that we could look downward. So we did that, and when we did, we discovered that we could see that polar plume of escaping gas. In this graph, everything its stuff is a function of time, measured through one orbit. And at the bottom, that circle is around where the conditions were right that we should have measured that polar plume if it was there. And the middle panel shows that little splotch inside the oval, which is the polar plume. High energy atoms escaping. The bottom panel shows that they're oxygen atoms with high energy. So we've detected the polar plume, and I want to show you that in just a little bit more detail because I think this is important. We have an instrument that can measure the composition of the gas and its energy, that is how fast it's moving. For your team members, that's the static instrument. And it's shown here where the different ions, the different atoms that are being measured are shown. This top blob is O2+, O+. We're measuring helium, hydrogen. And I want to draw your attention to the fact at the upper right it says this is a graph at 250 kilometers. These are the measurements in that polar plume at 250 kilometers. Now watch what happens as we go to 300 kilometers, 400, 500. The energy has increased. All of these blobs have moved over to the right. And at these energies, the gas is escaping from the planet. It's moving up at high speed. So we're watching the increase in speed as we move up. We're watching the acceleration of the ions in that polar plume as they're escaping to space. We're still in the process of understanding the processes, but we've seen the types of things that we're trying to see in order to understand the escape. What we want to do now also is add up all the atoms that are escaping. So how do you do that? How do you add up all the atoms that are escaping? Well, you just add them up. Imagine if this guy's head is Mars, and the solar wind is driving stuff this way. We drew an imaginary plane downstream of Mars, and every time the spacecraft passes through that plane, we count up the atoms that are escaping. So, God, what would be a good analogy? I'm stuck on this one. I can only think of stupid analogies. If you have a really powerful fan and a canvas that the fan is blowing stuff toward, and you sprinkle paint in front of it, the paint will hit the canvas. And if you add up how many spots there are, you can tell how much paint there was. That really was a bad analogy. But that's what we're doing here. This is the plane we've drawn, the square we've drawn downstream of Mars. On this graph, Mars would be about this big, between -1 and +1 on the other side of the room. And this is where we've sampled with the spacecraft so far. We haven't sampled the whole plane, but it's really hard. We've only got one spacecraft, and we've got only one plane, and only when we pass through it can we sample it. But every time we do, we add up the number of atoms. And you can see that here. This is the same graph, but it shows how many atoms. These are the ones going downstream that are escaping, but some are coming the other way. and we don't know that they've escaped, so we got to difference them. I'm not ready to tell you what the number is, because we're still calibrating the damned instruments. But this will tell us how much escape is occurring at the present epoch. So I've now told you a little bit about the results from the mission, and I want to finish with a brief discussion of how this fits into the broader Mars program that the Earth is launching, that we've got going. We have 5 spacecraft operating today orbiting Mars. Mars Reconnaissance Orbiter, Mars Odyssey, and MAVEN. Our NASA spacecraft, Mars Express, is from the European Space Agency. And the Mars Orbiter mission, MOM, is from the Indian Space Agency. All of these are collecting data. Opportunity and Curiosity are rovers on the ground that are collecting data. And they're trying to understand the Mars environment. The role of Curiosity and Opportunity is to answer questions that relate to the nature of habitability. Where was the water? How much water on the surface? To what extent was Mars habitable by microbes? The orbiters are finding out about the global perspective, about the history of climate, the history of water mapped globally. And downstream, so to speak, we're looking at the 2020 Mars rover, which is going to look a lot like Curiosity. The goal of the 2020 mission is to collect samples from places that can tell us whether there was life there, so that we can eventually return these samples to Earth and study in detail. Now, the 2020 rover won't return them. That's under that box labeled future planning, because it's way out into the future. The focus now is on getting that 2020 rover designed and built and launched. But the overall goal of the program is to answer these questions about life on Mars. Is there life? Was there life? If we find life on Mars, is it related to Earth life? You know, when I talked about these meteorites being transferred between planets, you can transfer life between planets inside of rocks. Or does it represent an independent origin? Well, I want to close just by coming back to MAVEN, because I've talked about the mission. What I haven't said, but I really have to, is even though I'm the person up here, there are a lot of people. Planetary exploration is a team sport, and it takes a lot of people to put a mission together. We've had about 600 people working on MAVEN. It's taken a dozen years from what I consider to be day one to launch, and I'm sorry, it was 10 years to launch. It's a dozen years to today. And a lot of people have put their heart and soul into it. Some of them in this room, a lot of them in this picture. The team is in the front in this photo. You can see way in the back there is the spacecraft. The spacecraft is important, but the team is really pretty important too. And I would be remiss to not really call your attention to them. My last chart, I want to say that MAVEN, this is my status chart, my walk-off chart. MAVEN launched on schedule and under budget, and you don't see those words associated with NASA programs that often. So I'm very proud of it. We came in about 10% under budget, and it's not because we over-budgeted in the first place. Everybody tells us we under-budgeted. It's because we made the right decisions along the way. The spacecraft and the science instruments are performing well. We are on track to be able to carry out our full science mission. We're about 5 months into the one-year mission, and right now all of my time is being spent writing an extended mission proposal so we can get a second year. We're hoping that we can go longer than that. We think we have enough fuel to last about a decade in doing science, and that would be spectacular because that would take us essentially through an entire solar cycle. And since it's that 11-year solar cycle, since it's the solar properties and processes and influence and energy that drives the upper atmosphere, that would really be exciting to see how the atmosphere responds to the whole thing. So all I can say is we're at Mars. Stay tuned. I've given you just a hint of what we have so far and of what's to come. You can continue to follow us on the web or on Twitter. And thank you all for coming out. It's just a delight to see you and to be able to talk to you tonight. Thank you. Questions? Yeah.
Bruce, without a magnetic field of any major size, you wouldn't expect much of a bow shock wave, would you? And wouldn't you then expect any water or atmosphere to be blown away rather rapidly in its evolution? I.e., how long did you think that there might have been water on Mars, and how long would it go away?
Those are really good questions, and that's what we're trying to answer. But in a nutshell, you get a bow shock like that on Earth because Earth has a magnetic field that deflects the gas around the planet. You get one on Mars because Mars has an ionosphere that serves the same purpose. It keeps the solar wind from penetrating, so the solar wind will want to go around it. And in deflecting it like that, it creates a bow shock. Without a magnetic field, we can strip off gas. You saw that video that I showed, and you saw some of the data that show gas being stripped off. The rates are really, really, really tiny today, just because the solar wind is not that intense. But the solar wind was more intense. The ultraviolet radiation was more intense early on. The number of storms, solar storms, was greater, and their intensity was greater. We think that all the action on Mars took place between 3.5 and 4 billion years ago. Mars did have an early magnetic field, and we think the turn off of that magnetic field allowed the turn on of solar wind stripping of the atmosphere, and the bulk of the atmosphere was probably gone in a few 100 million years. That's an hypothesis, and we're trying to explore that idea with MAVEN. Yeah?
How do the escaping ions pick up energy as they get further away from Mars?
The energy comes from the sun or the solar wind. The solar wind is coming in at typically 500, 400 kilometers per second, and it's charged particles. When you create an ion in the ionosphere, it can get picked up by the solar wind. It gets grabbed by it and dragged along with it. So you get a transfer of energy from the solar wind to those ions. The solar wind slows down a little bit, but there's so damn much of it, it doesn't slow down very much. And the ions speed up, and they get stripped away by the solar wind. Yeah?
So what would have turned off a planet's magnetic field?
Core froze out. The core froze out. On Earth, we have a magnetic field, and we think the driver is motions of the liquid outer core. And the motions are driven by heat released as the inner core is freezing. So if the whole core freezes, the motions stop. And Mars is smaller. Also, the freezing temperature is controlled by composition. We don't know what it was, but it's very plausible that it froze out earlier. I'm going to turn to this side. Yeah?
You said that the machinery for MAVEN was built over like 10 years. How do you account for changes in technology and things that, you start building something in year 1 and year 10, it's kind of obsolete?
Yep. You got it.
Okay.
We started 10 years ago in 2003. The design was really firmed up in about 2009. And after that, it was build it. And it does become obsolete. We would not build it the same way today. Some of the parts you can't get anymore. They're no longer being made. In fact, we had that problem during development where parts became obsolete or problems were discovered in them. If we were going to do it today, we would have to design it differently in order to account for what we know today and for what's available on the market today. But also what we know about how these instruments work and what we've learned in the last decade about Mars, where we might want to do things a little differently. Yeah?
The funding wasn't extended for continued science. Would the satellite or the spacecraft just continue orbiting without any function, or would someone be maintaining and collecting data?
there's a couple of subtleties here. First, it's in orbit. We're not doing anything with it. We're not going to bring it back here, for example. If we lost control of it today, or if we turned it off, which we're not going to do, but if we did, even in that thin, tenuous atmosphere, there's enough drag, the orbit would eventually decay, and ultimately it's going to hit the surface. The issue about an extended mission is, first, NASA wants to keep it going because they're relying on using us to relay data from the rovers. And there's a lander that's going to be launched in early next year that they're relying on us to relay. They're relying on us to be the relay in 2020 for the 2020 rover. And they're hoping we're going to survive a decade so that we can do that. We also want to do science, not just be a relay. And we're expecting they're not going to turn us off. But we're fighting to get enough money to do it right.
And the money would go towards paying the scientists to collect the data and do.
It's all people's salary.
Right.
It's the science team to plan the observations, analyze the data, reduce the data when it comes back, work any anomalies that crop up on the instruments, archive the data so other scientists can use it, and then analyze it and publish results on what they find out. But it's also the ops team, the people, some of whom are in this room tonight, who plan the observations for the instruments, the people who control the spacecraft, who do the navigation, track where the spacecraft is. All of them need to be paid. It's a fun job, but it ain't that fun to do it without a salary. And some people would. I want to eat every day, so I tend not to. But it takes roughly $30 million a year to run a mission like MAVEN.
Is there a lot of downtime or some downtime for you guys waiting for certain things to happen with the spaceship?
Sure doesn't feel like it right now. I'm running 24 hours a day, and my boss tells me, damn it, if that's not enough, I can work nights. Space science is a 9 to 5 job, 9 a.m. to 5 a.m. Yes?
The particles that are returning to Mars as opposed to escaping in the solar wind, why are they not escaping and where are they returning to?
We don't know the answer. Ask me in a year.
Okay.
I'm going to go back to this side. Yeah.
You mentioned a handful of meteorites that you were quite certain are from Mars. And I think I read once that most or all of the reason that we can say that is because of the isotope ratios that were measured by the Viking landers. Is that true or not?
Okay, here's the arguments. First, there are about 70 or 100 rocks. I've lost track. I remember the days when there were 2, but they've discovered a lot of them. They form what's called a clan in meteorites. They're all related to each other, and you can tell that by looking at the oxygen isotopes, the ratio of O17, 18, and 16 in the rocks. You know, the minerals have oxygen, and you can connect them all together. Some of them are young volcanic rocks. They crystallized within the last billion years. And that means that it has to come from a relatively big planet. Maybe the moon, but something the moon size or bigger. But those oxygen isotopes rule out the Earth and moon, absolutely, uniquely. That leaves the most plausible places as Mars or Venus. And dynamically, it's easier to get off of Mars than Venus and get here. But the clincher is what you said. There's a component of trapped gas within the rock. It's thought to be atmospheric gas that was implanted into the rock by the shock from the impact that ejected it into space. And that gas is identical in composition to the Mars atmosphere and distinct from any other source of gas in the solar system that we know about. And that includes the ratio of nitrogen 15 to 14, which is a good indicator of Mars. So either they come from Mars or we don't understand anything about gas in our solar system. I find it, I can't prove it, but it's like the sports writer Damon Runyon said, the race may not always go to the swift nor victory to the strong, but that's the way you bet. So in this case, the evidence points to that. I find it pretty compelling, but 99%, 99.9%, good enough for me. Good enough for me to go out and spend my hard-earned money to buy a rocket from Mars. Yes?
You mentioned calibration hasn't completed yet. How involved is that?
The instruments have a lot of subtleties. The ones that measure the composition of ions or of electrons, and every time you launch one and put it in a new environment, you've got to figure out how it works. So we're still learning how these instruments work. We're 7 months in orbit, we're 5 months into the primary mission, and we're still figuring it out.
What do you calibrate it against?
Some of them can be calibrated against each other, and some of them you just need to understand what it is that it's measuring, because it doesn't send back a number that is labeled oxygen abundance. It sends back a number of counts, and you got to figure out what is it it's really counting. And sometimes you see things that you didn't expect, and you've got to figure out how it's behaving. We've had to do a number of experiments on the spacecraft where we do something different with it to see how the instrument responds. Point it in a different direction, or run the instrument in a different way.
Can you compare it to similar instruments here on Earth, or to things from the rovers?
Not really, because it's a completely different environment. That's why it's a bit of a struggle.
Yeah.
We're getting there, but it's taken a lot of effort. Yeah.
Has the spacecraft done any deep dips yet? And can you describe what you guys were planning as the deep dips?
Sure. We call them deep dips. If you remember, I said that the lowest altitude is 150 kilometers. We actually target toward an atmospheric density rather than an altitude. So every week we decide if we have to move that altitude up or down a few kilometers to adjust. So we've been as low as 130 and as high as 170 at that nominal altitude. But we planned 5 deep dips where we dropped that periapsis, the lowest altitude, by about 25 or 30 kilometers. And it doesn't seem like much, but that gets us the rest of the way through the upper atmosphere down to the top of the lower atmosphere. And there's some very specific things that happen there. And it lets us make a connection between what, for example, Curiosity is measuring at the ground and what we're measuring at the top of the atmosphere. So we've now carried out 2 deep dip maneuvers. We drop periapsis, we keep it there for 20 orbits, about 5 days, and then we raise it back up. The second deep dip is just ending today. In fact, we had our OTM decision meeting on what maneuver we were going to do to finish the deep dip today at 6 o'clock. So that maneuver is going to be carried out about 11 or 12 tonight, Mountain Time, and that will be the end of the second deep dip.
You just fired the thrusters for a few seconds to get it back up?
Yeah. We do it at the highest point of the orbit. We fire the thrusters, and that adjusts the altitude at the lowest point. And it's a couple of minutes, actually, because we use our low-velocity thrusters. So they fire for a couple of minutes. We're doing about roughly a 5 meter per second burn. We change the velocity by 5 meters per second, and that gets us in or out. Yes?
The canals that you mentioned up front, how do we know that it's water that formed those versus another liquid?
The possibilities, first to mention them, liquid water, liquid CO2, liquid sulfur dioxide, wind, lava. I'd be hard-pressed to come up with another liquid or fluid in the case of wind. But those are the ones that I think work. And I'm going to use what I consider to be a pretty technical argument to point toward water. So follow along. We think it's carved by water because they look like they were carved by water. Did I go too fast for you?
We're following you there.
I mean, it sounds flip, but water is the most plausible liquid geochemically, cosmochemically. And now that we have rovers on the ground, we have evidence that water has been there. We measure water in the atmosphere. It looks like it was water carved, the shape, the size. It's the most plausible. Again, falling back to what's most plausible. I can't prove it, but it sure makes the most sense. And any other answer is more difficult. Paul again. I'm sorry, you've already asked a question. Judy.
Yeah, just an observation. When you look at the pictures of Mars, there's the 3 volcanoes, and there's a 4th volcano, and then there's a gash, you know, the canyon, which is the length of the United States. That's a pretty big, you know. They're all on one side. And to me, it looks like a pressure release of some kind, you know, like were these volcanoes all at one time? Were they at different times?
No.
When did the canyon develop, or can you even tell that?
You can get relative ages and good guesses at absolute ages of different terrains by counting up how many impact craters there are on them. If it's been exposed on the surface for a longer time, there are more impact craters because stuff is coming in all the time.
Yeah.
And what we learn is that Mars has been geologically active throughout its entire history. Those volcanoes that you mentioned took billions of years to form.
Okay, they weren't all at once.
No.
Okay.
And you know, it may have increased in intensity and then decreased, but all the activity isn't on one side. Those features are on one side. There's a different way that the planet is divided up. The northern hemisphere tends to be smooth, younger plains. The southern hemisphere tends to be old and heavily cratered. So why is that? It may relate to the interior dynamics, and that's what the InSight lander next year is going to learn about, the geophysics of the interior. Understanding the history of Mars is very complex because Mars is a complex system. You have think of it as the geology at the surface, the interior, the geophysics of the interior, the atmosphere, the upper atmosphere, solar wind interactions. All of these play together in complex ways to give us the environment we see. And with MAVEN, we're exploring a part of the Mars environment that hasn't been explored before. Each mission that we sent over the past 20, 30 years is exploring a part of Mars that is worth exploring and gives us a piece of the puzzle, but not the whole puzzle by itself. And by adding these all up, we're hoping to get a good understanding of the planet as a whole.
Yeah, you mentioned the discovery of that permanent metal ion layer. What are the challenges in determining the source of that? Is it like an equipment limitation or a priority issue of the mission? Or something else?
This is a case where we weren't expecting it, and we're going to study it with what we got, but we may not have the best instruments to observe it. I'm anxious to hear whether we've seen it during the second deep dip. The permanent layer we saw during the first deep dip we did. We got down to a low enough altitude, we detected it. I don't know if we've seen it during the second deep dip. I've been focused on the operations rather than the science. We have a science telecon tomorrow, and I'm hoping to hear what people have seen. But it's getting enough different measurements, getting enough different geometries that we can put it together.
So you think it's just a matter of time then?
Absolutely. Paul.
Simplistic question, but how in the world do you measure the location of your spacecraft down to 130-kilometer resolution when you have no detectors out there on that planet? You're a long way away. Just how do you do that?
We have radio antennas here on Earth. And when we transmit and receive, we can time how long it takes the signal to get there and back. When we look at the signal, we can tell the velocity of the spacecraft by looking at the Doppler shift of the signal. So what we really measure, the most useful thing is you measure the velocity. And by measuring the velocity throughout an orbit, you can determine the size and shape of that orbit very precisely.
So it's an indirectly calculated value.
Yeah,
Without any external calibration.
I'm going to say yeah, but that's not quite true. In the end, we can get our location accurate to about 1 kilometer. But we can't do much better than that with our spacecraft. But we don't need it better than that. Last question, anybody? Going once. Yes, sir.
In measuring the number of particles going in or out, the driver for that is the solar wind, which is sometimes highly variable. How do you work that out?
The question is when we're measuring particles coming in and out, driven by the solar wind can be highly variable, and how do we factor that in? Is that right? We have instruments to measure the solar wind. That's why we have 4 instruments that look like they're trying to understand the sun and not Mars, because we measure the different components of the solar wind and solar storms, solar flares as they get to Mars. The problem is we aren't always upstream of Mars where we can measure the solar wind directly, because we're in an elliptical orbit. Sometimes we're in back of Mars. So we have to piece it together as best we can. Again, thank you all for coming out. It's my pleasure anytime to talk about MAVEN, and it's a delight to be able to talk about what we're getting out of it rather than what's coming up. So thank you very much.